G'day guys, Socket here. Today we're going to continue on with part 2 of our amplifier tutorial series and pick up where we left off in part 1 when we were talking about watts, amps and ohms. And in today's episode we're going to just continue on where we're looking at the practical application on those terms, including some formulas and things that we can use to calculate stuff like amplifier wattage and fuse ratings and and a few other bits and pieces. So if you enjoyed part 1, part 2 is going to be more of the same. For those that are already across all this stuff, feel free to jump ahead in the series. As I said before, we'll catch up to you guys a little bit later. So without any more introduction, let's jump into part 2. Well, let's work through them one at a time, starting with a term that we use a lot in car audio, which is the term watts. So we talk about a 200 watt speaker, or my amplifier puts out 1,000 watts per channel, but what do we actually mean by the term watt? Well, if you think about the electrical devices that we have around us, like your television, your oven and your toaster, or a light bulb or whatever, all of these electrical devices need power or electricity to operate, right? I mean, if they don't have power, they just kind of sit there, but once you turn on the electricity supply, then they light up, heat up, turn on, play music, whatever it is that they're designed to do. Now, clearly all different electrical devices require different amount of power to operate, and so for example your oven is going to require more power to operate than a light bulb, right? If they're operating for the same amount of time. So for example, you'll hear that your oven is a 2,500 watt oven, right? Or your kettle might be a 100 watt kettle, or your light bulb might be a 30 watt light bulb. All right, so the term wattage is used to describe how much power the device needs to operate. So when we're talking about car audio and we're talking about my amplifier can supply 500 watts per channel, that means that the amplifier can supply a certain amount of power to whatever device it is driving. So for example, if you have an amplifier with 500 watts per channel supplying two 200 watt speakers, it means that it will have plenty of power because it's supplying 500, the speakers only need 200, and therefore it's got more power than the speakers need. And it doesn't mean that when you turn the amplifier on that it's sending all 500 watts to the speakers. The speakers will simply take, or that's not the right term, but the speakers will use whatever wattage that they need, depending on where you've turned your volume controller up to. So if you've turned it all the way up to 100% and they're running flat out at 200 watts, then they will be drawing 200 watts worth of power from that 500 watts that the amplifier has available to supply them, right? And we call that additional wattage over what your speakers are demanding what we call headroom, right? So that is what we mean by the term watts. Okay, so let's talk about the next term, which is the term voltage. So we're familiar with voltage when we think about batteries or electricity supply in your home. We know that we have a 12 volt battery in our car, or we need a 1.5 volt AA battery to run our flashlight, or we can get 110, 120, 240 volts of electricity out of our power sockets in our homes, right? But what do we mean by volts? Well, the easiest way I like to think about it is, thinking about an electric shock. If I put my fingers around a 1.5 volt battery, I can't really feel anything in terms of electrical shock. But if I'm connecting my jumper leads up to my car battery, often I will get quite a spark when I touch the clamp onto the, for example, negative terminal of the battery, right? So clearly 12 volts has a lot more electricity than a 1.5 volt battery, right? And if I stick a fork into a power socket in my home, and I don't recommend that to anybody. It could potentially kill you, right? So when I think about volts, I think about the amount of potential power supply that's going to come out of a power source when I connect up the circuit, right? So if it's a small voltage, then I'm going to get a little bit of power. If it's a large voltage, I'm going to get a lot of power. And so if I connect a high voltage to my circuit, it's going to push a lot of electrons, I'm going to have a lot of current, and I'm going to have a lot of electrical energy flowing through that circuit to be able to power the devices that I've got connected to that circuit. And so the higher the voltage, the higher the energy. Okay, so now we've had a talk about volts. Let's talk about the next term, which is amps. So unlike volts, amps is simply a measure of electrical current, or the number of electrons that you have going around an electrical circuit at any particular point in time. It measures the strength of that electrical flow through a wire. So it's in itself, you can't really adjust amps. It is the result or the measurement of the electrical flow caused by the voltage that you're applying to a circuit. So another way of thinking about this is amps is kind of like measuring the speed at which athletes run around a running track, right? That's the best way to kind of think about it. Now, if there is 0 amps, it means that you have 0 current flow. So while you might have voltage, unless the electrons and you have an electrical current, you won't be able to supply any power. So when you look at the term power, we talk about power being measured in terms of volts and amps. You need a certain level of voltage and you need a certain level of current flow to be able to provide the power to the speakers that you need. So amps is an important measure, but it's not something that you can adjust by itself. It is a function of the number of volts that you're adding into an electrical circuit. So the last term that we want to talk about is the term resistance. So resistance refers to how difficult it is for electrons to move through the conducting material or around a circuit. And so, for example, we use copper wire because it's a good conductor. The electrons can move quite freely through copper. Gold is better, but of course it's too expensive to make all your wiring out of gold. That's why sometimes on high-end electrical equipment you will find that they use gold connectors and things like that. But in my opinion, that's more of a marketing ploy than anything else. But certainly things have different levels of resistance. So if you're using tungsten or something like that, that we find in, light globe filaments and stuff like that, they are it's very difficult for the electrons to move through that material because it has a lot of resistance. And in fact, we use that so that we can generate light and heat and other things. But resistance is simply a measure of how difficult it is for the electrons to flow through. Now, all electrical circuits have a certain degree of resistance. There is no such thing as zero resistance. People are trying to create superconductors and things like that with zero resistance, but in the real world they don't really exist, and particularly in car audio. So where we see resistance in car audio is in a couple of places. One is in the speakers. So, you've heard of a 2 ohm speaker or a 4 ohm speaker. That is describing the amount of resistance that the speaker has. So you'll require more power to drive a 4 ohm speaker than a 2 ohm speaker, and that's to do with the speaker design, how sensitive it is, how easy it is to move the voice coil against the magnet, and all of that type of stuff, the stiffness of the cone. And so that is one measure of resistance. And while we're talking about speakers, we can talk about the sensitivity of a speaker. So, the sensitivity or the efficiency of a speaker, some of them are rated at 85 dB, some of them are rated at 92 dB and higher. The higher the sensitivity or efficiency of a speaker, the less power they need because they are less resistant. And so a 92 dB speaker will give you more output per watt than a 85 dB speaker with the same wattage, because the 85 dB is more resistant. And then finally, while we're talking about speakers, we have a special term which we call impedance. And so when you're playing a speaker, the impedance or resistance of the speaker will go up and down because of the different frequencies and how long you're playing those frequencies for. So the resistance or impedance of a speaker changes while playing music, and it's the job of the amplifier to constantly change the voltage going to the speaker to make sure that the volume level stays the same all the time as the impedance or resistance of the speaker changes while it's being played. Now, the second major area of resistance when it comes to car audio is the gauge of the wires. So, we have everything from 0 gauge down to, 24 gauge. And so the gauge of a wire is basically how thick it is. And depending on how many electrons or how much current you're trying to pass through your electrical circuit, your wires have a provide resistance. So and that's to do with one, how thick they are, or its gauge, and then the second one is the length of wiring that you're running your current through. So the longer the length of your wiring, the more resistance you have, because the electricity has to push through more copper or more conductive material. So a 10-foot strand of cable is going to have more resistance than a 2-foot strand of cable, for example, right? And on the same token, a thick cable like a 0 gauge is going to be able to carry more electrons and more current than a 8 gauge wire, which has a much smaller cross section. Okay, so that is the topic of resistance. So now that we've got our heads around these common terms, let's go and look at some real life practical examples of how we apply these terms in car audio. So let's take our circuit that we've been looking at and replace our light bulb with a car audio speaker. Alright, so one of the questions that we might have is, how many amps do I need to run my speaker? Well, a speaker is an electrical device just like a light bulb. If you don't give it any power, it won't make any sound. So it's incorrect to think that speakers somehow draw power from the power source. It's quite the opposite. The power source pushes or supplies power to the speaker, and the amount of power that is provided to the speaker is controlled by the volume knob. The more power you give to the speaker, the louder it will play, and if you keep sending it more and more power, it'll get to the point where it will start to start smoking, and eventually, boom, will catch on fire, right? But to run your speaker safely and not get into this position, how do you work out how many amps that you need? Well, let's say that I've got a 500 watt speaker and I'm playing it at 50% of its maximum volume, so the speaker needs about 250 watts of power. And let's say that I'm running this off my my battery, which has, is fully charged and is at 12 volts. Well, what current flow or amps do I need to maintain a 12 volt supply to the speaker? Because it is the volts that actually make the speaker cone kind of move in and out. Well, we can answer that by just using the formula that we looked at before, watts equals volts times amps. So in this case, it'll be 250 watts divided by 12 volts, which gives us 20.8 amps. Okay, so happy days, right? So we need 20.1 amps or 20.1 amps of current flow to maintain 12 volts of power at this speaker to run it at 250. So if we're running, this speaker and we're playing music or whatever, and we want to maintain it at 250 watts of output, and I'm running it at my 12 volt battery at nearly 21 amps, how long will my battery last? Well, that depends on, first of all, how big your battery is, and your battery is generally measured in what we call amp hours, and that can range from a small battery of 40 or 50 amp hours all the way up to quite a large battery of maybe 120 amp hours. But let's pretend that we have a 50 amp hour battery in our car. So our running time will equal the battery amp hours divided by the number of amps that we're running. So in this case it will be 50 amp hours divided by 20.8, which will give us 2.4 hours, or 2 hours and 24 minutes before our battery is kind of exhausted and will be flat. So there's a couple of examples of how you can use these calculations and the information that we've looked at to work out your power supply and how long that will last when running your audio system. So another kind of problem that we can sort out is, what size fuse do I need for my circuit? If I know my wattage and how much power my devices need, and I know the voltage of my circuit and things like that, or the amperage of my circuit, then I can work out what size fuses that I need. So let's use the example again. So before we have our 500 watt speaker and our 12 volt battery, and before we were playing it at 250 watts, or about half of its maximum volume. What about we turn it up to 90% of its maximum volume, or 450 watts? So now we've got watts equals volts times amps, which will be 450 divided by 12, which will give us 37.5 amps. Now if we have a 30 amp fuse in the circuit, and we're putting 37.5 amps through it, well, of course, boom, there goes the fuse, right? And here's a good example. When we were running at 50%, the fuse was fine, but as soon as we turned it up to 90% and we were putting a lot more current through the circuit to supply the electrical energy or the power that we needed to run the speaker at 450 watts, it exceeded the amperage of the fuse, and the fuse melted. And so in this case we're probably going to need a 40 amp fuse in the circuit, not a 30 amp fuse. Okay, so far we've been talking about power supply, but one of the things that we haven't talked about is the effect of speaker resistance. So let's take our little circuit that we've been talking about. We've got our speaker here, our 500 watt speaker that we're running at 50% volume, so it needs 250 watts of power. And let's say that this is a 4 ohm speaker. Well, how does this affect our power supply? Because we've got 4 ohms on this speaker. And so the way to work this out is we use this formula here, that we've got to take the power of in watts and work out how many volts that we need to supply this. So that's power by the volt squared divided by resistance, means volts is power times resistance square root, and that tells us that we need 31.62 volts. Once we have the voltage, we can then work out the number of amps that we need, and that tells us that we need 7.91 amps at 31.6 volts. But hang on one second, how does that work? We've only got a 12 volt battery. How can we get, how can it supply 31.6 volts? Well, if we just left our voltage at 12 volts and we tried to sort of work out how many volts that we could supply this 4 ohm speaker, and we do all the calculations, it tells us with 12 volts we would only be able to supply 3 amps, and supply this speaker instead of 250 watts, the most we could supply it with a 12 volt power supply would be 36 watts of power through a 4 ohm speaker. So that would be about, let me think about that, 20%, 15% of the speaker's total volume. So what is going on? Well, this is where an amplifier comes in, right? An amplifier takes care of this problem because it takes our 12 volt and amplifies it up to 31.6 volts that we need, and it also has what we call a current gain. It's able to adapt the amount of current that is flying through the circuits because it stores power inside capacitors inside the amplifier. So it does two things. It works out exactly how much voltage and amp combination that we need to supply the 250 watts, taking into account the power that we need to overcome the 4 ohms of resistance, and gives us the 250 watts that we need for the speaker. And while the speaker is playing and creating impedance and fluctuating in terms of its internal resistance, the amplifier is taking that into account as well and giving us the voltage and amps that we need to keep the speaker playing and operating, and importantly not changing in volume level. And so what you may not be aware of, which I found surprising as well, is that modern amplifiers will take this 12 volt voltage from your battery or your power supply, car power supply, and it can spike 20, 30, 40, 50, 60 volts, right, to give you the voltage that you need to drive your speakers. So one of the questions that this stuff can help us answer is, what gauge of wire do I need? Now, we looked earlier at the example of a 30 amp fuse failing because we put too much power through the circuit, and that's exactly what they're designed to do. They're designed so that if you exceed a certain amount of electrical current running through the circuit or a certain amperage, then the wire will fail, or the fuse will fail and melt and protect your equipment. But small gauge wire acts kind of a little bit the same, right? So you have, within the wire, you have these electrons sort of moving through them, and when you increase your amperage, when you increase your voltage and you're increasing the current flow, you're essentially putting more and more and more electrons through the same wire. And if you keep putting more and more electrons through, they're being forced closer and closer together, and they start bumping into things and they start causing friction, which generates heat. And and that's why your wires kind of warm up. And if you push too much electrical current through those wires, they'll go from just warming up to actually catching on fire, or just melting, or failing in some way, right? And that's where wire gauge is important. So one of the things that we use to determine what type of wire gauge that we need is we use a wire gauge chart. Now, wire gauge comes in two forms. There's the metric form, which we measure in millimeters, or there is more commonly used what we call the American wire gauge. And so we have 8 ADG, or 1 ADG, that's 8 gauge or 2 gauge, and AWG stands for American wire gauge, right? So the bigger the number, the smaller the wire. So a 12 gauge wire is thinner than an 8 gauge wire. Now, you've probably heard of 0 gauge, which is typically used for this big thick stuff, which is used to for power supply for your amplifiers, and that's good up to about 150 amps. But there are bigger wire gauges than 0 gauge. There is 20, 30, 40. In which case, the bigger the number, the bigger the 0 wire gauge. And so when you're reading these charts, you need to kind of look at two things. You need to look at the length, both the amps that you want to deal with and the length of wire run that you want to run, because the longer the wire, the more resistance that they're going to be. So when I'm looking at this particular chart, it's sort of running up to 6 feet to 2 meters, or 10 feet to 3 meters. So I just pick the appropriate row that contains the length of wiring that I'm looking at, or the length of the circuit, and then I run my eye across to the amperage that I need. and that will tell me the wire gauge that I need. So let's do a practical example. So I have a 500 watt amplifier, and I want to figure out what gauge wire I need to attach this amplifier for its power supply, right? So what I need to do then is I need to first work out how many amps this 500 watts will be, and so I can work that out by working out the currents using the formula. Current is power divided by voltage, and it tells me I need 41.67 amps, right? Which means I can then go to the wire gauge chart. I know this is going to be a short run of wire, 10 or 15 feet long, and and I can run my eye across to where it's 41 point, always easier to go up one than down one, right, or whatever. So I'm going to choose a 50 amp fuse, because if I make it a 40 amp fuse, it's probably going to trip out because it's below the 40 amps is below the 41 that I need, so I'm probably going to go up to a 50 amp fuse. So in this case, I'm looking to use a 6 gauge wire, right? So that's this one here. Now, one thing to keep in mind when you're shopping for wire is that not all wires are created equal. The cross section shown in this chart is the metal part of the wire. It excludes the insulation. Now, some brands cheat, and give you a 6 gauge wire, but it's actually only got 8 or 10 gauge worth of metal. So make sure you check before you purchase. Otherwise, you risk having undersized wire in your car and not even being aware of that. Okay, so now that we've been through some examples, it's time to just touch on one last important concept before wrapping up this tutorial. So far we've been simplifying things so that we can sort of follow the these concepts along without complicating things with reality. But one of the things that we do need to clear up is this term direct current versus alternating current. So direct current is where we have a circuit like we've been using in the examples so far during the tutorial, where we have the a simple circuit where we have the electrons sort of flowing from the negative terminal through the light and back again. This diagram actually has them the old way that we were taught, but that's not the way it works. But the electrons is flying around in a simple circuit like this, like we do with our car battery, all flowing in a single direction. Now, if we applied a direct current to a speaker, it wouldn't move in and out. And people sometimes use this to test speakers. All it will do was push out and stay there while we have the current applied, and and then sort of return back to its resting position when you remove the current. But it certainly wouldn't move in and out like a speaker playing that we're kind of used to, right? For that, we need to use a thing called alternating current, right? So alternating current is different to direct current because it switches back and forward, right? It changes direction back and forward many times a second. And in Australia, in our houses, our alternating current is switching polarity, at 50 hertz or 50 times a second. So it is this back and forward motion of the alternating current that allows our speakers to actually move in and out. Okay, so when we've been looking at these examples, we've been using a direct current example, but in reality, speakers require a alternating current to operate. So, well, that's really interesting. So not only do our amplifiers take care of making sure that our speakers have the right voltage and amperage to be able to run, they are also taking care of taking our 12 volt power supply, which is in direct current format, and converting it to an alternating current format so that our speakers can move in and out. So yeah, these little amplifiers are pretty amazing things. So guys, that brings us to the end of another tutorial. I hope that you found the content interesting And as always, if you've got a comment or a question, please chuck them down below. I'll see if I can get back to you as soon as I possibly can. But that takes care of all the technical stuff around electricity and the technical terms and formulas and things. In the next part, we're going to start looking at the at amplifiers and how they work, and get right into the details so that you can make some good choices when you're thinking about buying your own amplifiers. All right, so until then, I will catch you in the next episode.